Okay, so this video is on graphs in mechanics. So mechanics is an applied area of mathematics that's studied on the A-level course, and a lot of it will involve drawing graphs and sketching graphs and interpreting graphs. So I just want to talk about a couple of different types of graphs today. So the first is what's called a displacement-time graph. All right, so we've got displacement-time graph. And this is where we have displacement on the vertical axis plotted against time on the horizontal. Typically we use the letter S to represent displacement, but it could be an X. So just be careful, make sure you're consistent with the context of the question. And another type of graph would be what's called the velocity time graph. Okay, so that just illustrates velocity against time. And the third type then is an acceleration time graph. And right at the end of the course, when you've studied some calculus, we will look at the relationship between these types of graphs. Okay? But for now, we're just going to look at each of these separately. So velocity time, and then this is acceleration time. Okay. This is precursor to a constant acceleration graphs, which is what we're going to be looking at in the next video, or next videos to come. So first then, displacement time graph. So displacement time graph is where we plot the displacement of an object against the time from the start of the model. So in this case, the start of the model, which is when t is 0, typically, the start of the model, the object, whatever this is, it might be a particle, it might be a car, it might be, we don't know what it is starting a certain distance away from a relative fixed point. And all of these graphs are all relative to a fixed point. And we call that point the origin. Okay, it's all relative to the origin. So whatever this distance is, let's call it 20, say, could be anything. This particle is starting 20 meters from the point O, specifically in the positive direction. Now, I've just done a video on vectors, and I've said that displacement, velocity, and acceleration, they're all vector quantities, but we're just looking at a one-dimensional case. So actually, although they are vectors, it's not much different to distance at this stage, but there is still a subtle difference between displacement and distance. And that's that displacement can go negative. So this one here, let's say again, it starts at 20. At some point in time, it has arrived at the origin. So whatever t value this is, it's arrived at the origin. It's moved from 20 meters away and it's gotten to the origin, and then it's carried on. So its displacement has gone negative. And that is perfectly allowed in mechanics. Displacement can go negative until it gets to a point where it said, oh, I've kind of gone far enough and I'm going to come back round, and it arrives back to the point where it started. So just to give some kind of illustration to this, I've got an animation here. So I've got a point O, which is my fixed origin, and I've got a point A over here. This is the point of interest. And what's going to happen is when I start the time, this is going to move towards O, and all the time it's going to be in a positive direction. So we're taking to the right to be positive. So it's starting 20 meters away, and then as time moves on, it'll get closer and closer and closer to O until it gets to O, and then it'll just carry on going this way. And that's when the displacement is negative. Because I'm taking this way to be positive, and the particle is that side of O, then we say its displacement is negative. Okay, so that's what it means to have negative displacement. So let's just see it in motion. Okay, off it goes. There we go, getting closer to O, and then it goes through O and then comes back the other side. It's gone far enough, and then it comes back and stops. Well, it should stop at O. In fact, I just had this on a loop, so it keeps going backwards and forwards. Okay, there we go. But we can see that here the displacement is negative, 0, and then it's positive again. That's its most positive, and then it starts to come back and until it gets to 0 again. Okay, so displacement can be negative or it can be positive relative to a fixed origin. Okay. That's what it looks like to have a negative displacement. All right, velocity then. So velocity time graphs. Here we have what's called a linear velocity time graph. Linear, in this case, just meaning a straight line. And essentially, the velocity is steadily increasing. Okay, velocity is steadily increasing. Or we could say it's increasing at a constant rate, or something along those lines. And this is kind of terminology and phraseology that can come up in an exam setting, so you need to be familiar with it all. So velocity is steadily increasing is good terminology to be familiar with. This one here, the velocity is always positive, so it's always moving in the positive direction, but how fast it's moving in that direction varies with time. And we can see that for the first part of this, the motion, it is speeding up. So it's getting faster as it moves that way. But up here and down this side, it is still moving in that direction. It's still moving in the positive direction because the velocity is still positive. And it keeps moving in that direction, but it's getting slower and slower and slower and slower until at this point it stops moving. Okay. The velocity all the way through this motion is positive. But just like displacement can be negative, the velocity can also be negative. So if the velocity is negative, then it is moving in the negative direction, which is often depicted to the left, but not necessarily. Sometimes it's down if we're dealing with a vertical motion. So moving to the left is getting faster and faster and faster to the left until it gets to here, when it's going as fast as it is, as fast as it does, and then it starts to slow down, but still moving in the negative direction until it gets to here when it stops moving, and then it starts to move back this way again in the positive direction. Okay, so that's velocity time graph. So I've got a couple of examples now I'd like to go through. First one. A particle moves along a straight line. Okay, so this just means it's a one-dimensional issue. We've got one displacement variable against time. The particle accelerates from rest to a velocity of 15 meters per second in 30 seconds, and the particle then moves with constant velocity of 15 meters per second for 1 minute before decelerating to rest over a period of 5 seconds. Okay, so a couple of things to pick up on. First of all, it accelerates from rest. Rest is a mechanical word for the velocity as being zero. Okay, that's all it is. It just means the velocity is zero. We're told it accelerates from rest to a velocity of 15 meters per second in 30 seconds. Now that's enough information to answer part A of the question, which is to calculate the acceleration of the particle in the first 30 seconds. So by definition, oops, it's not used black, acceleration is equal to the change in velocity divided by time, or change in time. Just like the velocity is equal to the change in displacement over the change in time. So change in velocity, well, it's gone from 0 to 15. So the change in velocity then is 15. The change in time, well, it's taken 30 seconds to do that. So that's going to be divided by 30. So that's going to be a half. So that is 1/2 per meter per second per second. Part B then is to draw a velocity time graph of this motion. So that's the whole motion now, not just the acceleration part. But we know that this motion starts from rest, so that's when t is 0, v is 0, so it's going to start down here. And then in 30 seconds, it's going to be travelling at 15 meters per second. Okay, so let's call it that point there. That's a straight line between them because we are assuming constant acceleration. We're assuming constant acceleration. So this point here is 30 on my t-axis and was 15 on my v-axis. Right, back to the scenario. The particle then travels with a constant velocity of 15 meters per second for 1 minute. Okay, so it's at 30 seconds into the motion. So if it's going to travel this far for 1 minute, then it's now going to be at 90 seconds into the motion. So just be careful. It'd be really easy to put a 60 in there because it said 1 minute, but it's 1 minute of travelling at constant velocity. So that is going to be 60, more than the 30. And then finally, it decelerates to rest over a period of 5 seconds. Okay, and we're going to assume it's decelerating with constant deceleration. So that's going to be there at 95. Okay, fantastic. So there's my velocity time graph of my motion. And then part C, calculate the total distance travelled. Now, I've not talked about how to solve this yet. So the total distance of a velocity time graph is actually just the area. So the area is equal to the total distance. So we just need to add up our polygon. Now, you can split it up into the triangle, the rectangle, and the triangle if you want to, or you can just treat it as one big trapezium. I'm going to treat it as one big trapezium because then that saves on a little bit of calculation. So just to remind you, the area of a trapezium is the sum of the two parallel sides multiplied by the perpendicular distance divided by 2. So the area is going to equal 95, which is the bottom base, plus 60, which is the top base, the top length. That then gets multiplied by the perpendicular distance, which is 15, and that's all divided by 2. Plug that into my calculator. So I'm going to get 95 plus 60. That then gets times by 15, and that's divided by 2. So the total distance travelled is 1,162.5 metres, or 1.2 kilometres to the nearest 1 dp. Okay. Second example. I've not got the wordy context to this, but we've been given a velocity time graph. So the previous example we had to draw the velocity time graph, which is something that you need to be able to do. But this time we're given the velocity time graph, and instead of finding the displacement, or the distance this object has travelled, we've now been given the displacement and we've got to find an unknown time. So in this case, what I'm going to do is I'm going to add up these three areas. It's going to be a function of t, and I know that that area must be equal to the displacement, which is 1,425. And that will give me a linear equation in t to solve. So this is a trapezium, so that's going to be 10 plus 20 multiplied by 20 divided by 2. That's the area of that trapezium. Plus the area of this rectangle, well, that's going to be 20 high multiplied by t across, so it's going to be 20t. And then that's going to be added then to this triangle. And an area of a triangle is the height multiplied by the base divided by 2. So that's going to be 20 times t on 2 over 2, which is 5t. Okay, so 20 high times t on 2, well, that gives me 10t. That will then give me the area of this rectangle, so divided by 2, so 5t. And that I know equals 1,425. That's a nice linear equation in t, which I can go ahead and solve. So the coefficient of t is going to be 25. And then the number on the right-hand side, well, that's going to be 1,425 subtract 30 times 20 all over 2. That's going to be 1,125. And then divide by 25 to give me that t is 45. And that's in seconds. And I know it's in seconds because this is in meters per second, this is in seconds, and this is in meters. Okay, so all of these units all agree with each other, so therefore the time remains in seconds. Okay. Thank you for watching.